Hello friends, today we'll discuss what is finite automata in detail. Before we start with the finite automata, we need to know certain prerequisite for this finite automata. So let's start with sets. What exactly mean by set? As this definition says that a set is a collection of objects. Now these objects can be any member of this particular set, like it can be a collection of 4 letters like A, B, C, D. So it is finite collection of elements, which is written as L is equal to A, B, C, D. So this becomes a set, and whatever the elements of these set are there, these are also called as the members of this set. Moving ahead, to understand what exactly set is there, we'll now look into the various operations on the sets. So to begin with, let's talk about union operation. Imagine I'm having set A, which consists of elements like A, B and C, and there is set B, which consists of elements like E, D and let's say F. Now when I write union of these two operations, I can write A union B. What it consists of? It consists of the elements from set A as well as set B. So I'll write the elements from both the sets, that is union of these two elements, these two sets, that becomes A, B, C, D, E, F. Imagine I'm having another set called as B1. I'll keep A as it is, but I'll write down another set called as B1, which consists of the elements like A, D and F, for example. So how can I write union of these two elements? It is A union B1. So the union of these two sets will be, now you can see in set A there is a common element called as A, so we'll not repeat that element, we'll write that element only once. So that is A. Same B element which is there in only A, same element C, and whatever elements are there in B1, we will copy all those elements A, B, C, D, F. This is union of A and B1. Now let's talk about the intersection. Let's talk about another operation that is called as intersection. We can write this intersection operation like A intersection B. How can we write? So we'll write the elements which are common to both these sets. These will come under intersection. For example, if I'm having A is equal to, these are the 3 elements I'm going to write into set A, as well as set B consists of, for example, A, D and E. Now A intersection B will become A. The elements which are common to both these sets, that is intersection. Let's move on to the third operation, that is called as the set difference. Set difference, we can write set difference as A minus B. It indicates that this operation or this set will consist of elements which are present in set A, but these elements which are not present in set B, those elements will be there in set difference. For example, suppose I am having set A as A, B and C, and B is equal to, let's say I'm having A, D and E. So A minus B will consist of the elements which are present in A but not present in B. If you talk about element A, it is present in both the sets, so that will not come into picture. B is present in A but not present in B set. So I'll write down this B. Similarly, set A consists of element C, but that element C is not present in set B. We'll write down that. There are no remaining elements in A. We'll stop it here. So this is the set difference between these two sets, that is set A and B. Moving to the next operation, that is complement of A. It is written as A bar. This consists of the elements which are not present in A. All elements present in A will not be there. Other than that, all elements present will be there into A bar. So this is called as the complement. Now we have discussed some of the operations on sets. Now we need to understand certain terminologies to look into the finite automata. So to begin with, disjoint sets. Now what exactly you mean by disjoint sets? The definition says that if 2 sets are there and these sets do not have any common elements, this is called as the disjoint set. For example, if I'm talking about A intersection B is equal to 5, that means I do not have any common element between A and B. That is called as the disjoint set. Then next is cardinality. What exactly you mean by cardinality? It is the number of elements of that particular set. That is called as cardinality, and it is denoted as mod of A. So it tells me the number of elements present in that particular set. And next important terminology we need to understand, that is power set. So power set, it is written as, suppose I'm having set A, the power set of A, it can be written as 2 to the power A. It includes the all possible combinations of the elements of set A. For example, I have a set, let me take an example and then I'll explain. Here I am having set A that consists of elements like 1, 2 and 3. Now I want to find out the power set of this A, 1, 2, 3. Okay, it is denoted as P of A, that is power set of A. How can I write down power set of A? As I said earlier, it consists of all possible combinations of elements of A. That is power of A, it is equal to 5. I don't have any element, that is empty set, what we call it as. Then I'll take single element from A. So that is 1 I'm going to write. Then second element, third element, and then combination of these 3 elements, like I can write 1, 2, then 2, 3 and 3, 1 or 1, 3. And then final combination of all these 3 elements, that is 1, 2, 3. The number of elements in the power set will always be 2 to the power cardinality of that set. What is cardinality of this set? That is 1, 2, 3, 3. So it becomes 2 to the power 3. So this power set will consist of total 8 elements. Suppose you are having total 4 elements in this particular set, then the total number of elements in power set will be 2 to the power 4, that is equal to 16. So keep this in mind. Now we need to understand few basic terms to move ahead in the finite automata. That is strings and languages. So before we understand strings, let's talk about alphabet. What exactly alphabet? Now this alphabet is nothing but set of symbols. To be particular, it is finite set of symbols. That symbol can be anything like 0, 1. If you talk about English language, I can have, let's say, 52 total symbols. 52 in the sense that I am writing capital A to Z and small a to Z. So this 26 plus 26 total, 52 symbols I am considering. So that becomes alphabet for English language, for example. And 0, 1 becomes an alphabet for the binary language. So to summarize, an alphabet is nothing but collection of symbols. It is finite collection or finite set of symbols. So that becomes alphabet, and this alphabet is denoted by a symbol sigma. Henceforth, when we will be referring to an alphabet, we will be using a symbol called as sigma. Next is string. Now, when you define a string, it is actually a finite sequence of symbols. Because whenever we are talking about a string, the number of alphabets in that string should be finite. So string is a finite sequence of symbols. Now where these symbols will come from? From the alphabet, right? So we say that it is a collection or finite sequence of symbols from that alphabet, and it is called as a string made up of the symbols over this sigma. And that's why we define a string like a string over an alphabet. So this is my alphabet which comes from sigma. Let's take an example. If sigma is equal to 0, 1. So 0, 1 is my alphabet. What I'll be doing is I'll be taking combination of these symbols from this sigma, which is going to be a finite sequence. So this is my string, which is a finite sequence over this alphabet, that is 0, 1. So it is called as a string over sigma. Let's take another example. If sigma is equal to AB up to Z, then any combination of symbols from A to Z, we call it as a string over this sigma. A sigma is nothing but A, B, Z. But remember, to repeat again, string is a finite sequence of symbols. Next is length of a string. Simple. It is the number of elements in that string. So that becomes length of the string. Finally, empty string. When we speak about length of the string, I am having some elements into this string. That is, you can see there are 5 elements I have counted. That is the length of the string. In some cases, you might require that I am having a string which has got length equal to 0. That is called as the empty string, and this empty string is denoted by a symbol called as epsilon. So epsilon denotes an empty string. Another important term we need to know, that is called as power set. Powers of sigma. We have understood what is sigma. Sigma is an finite set of symbols. So that is our sigma or alphabet. Now, whenever I want to take some combinations of this sigma, we need to speak about power of sigma. That is represented as sigma to the power k, where k is any positive integer. What it says that sigma to the power k, it indicates that it is set of strings which are having length equal to k. As I said, k is nothing but a positive integer. Let's take an example. Sigma is equal to 0, 1. Now, when I write sigma to the power 0, what does it indicate? It indicates that this is a set which consists of strings with length 0. What is the string of length 0? We have seen in earlier slide. It is sigma. Sorry, it is epsilon. So I write sigma to the power 0 is equal to epsilon. Epsilon is a string with length 0. Then sigma to the power 1, as it indicates that 1. I am having the strings which are having length equal to 1 over this sigma. What is sigma? 0, 1. So I'll be picking up 0 as a string, 1 as a string. Moving ahead, sigma to the power 2. I want to have a set which consists of strings with length 2. So any combination of these 0, 1 having length equal to 2. So that is 0, 0, 0, 1, 1, 0 and 1, 1. Likewise, keep on continuing. If I generalize it, sigma to the power k, I'll be having a collection of strings whereas the length of each string will be equal to k. And these strings will be made up of this sigma, that is 0, 1. So it says that sigma to the power k is equal to some strings that says that each string is of length k. Now we need to understand a few more terms about this sigma. We have written or we have seen sigma to the power k. Okay, it says that I am having a set of strings which are having length equal to k. Let's keep on going ahead. Now I am going to write sigma to the power star. Star means 0 to infinity. Okay, so how can I write this star? If I write sigma to the power star, which is nothing but it will consist of the strings of any length, because sigma to the power star I can write sigma to the power 0, sigma to the power 1, sigma to the power 2 and so on. And all these sets will be combined together by using union operation. So to summarize, I can write sigma to the power star is equal to sigma to the power 0 union sigma to the power 1, sigma to the power 2. Now what is this sigma to the power 0? We have seen in earlier slide. Sigma to the power 0 is set of strings with length 0. Sigma to the power 1, set of strings with length 1. Sigma to the power 2, set of strings with length 2. 3, 4, 5 up to infinity. So this set becomes infinite. If I take an example, sigma is equal to 0, 1, then we can have sigma to the power 0 is equal to epsilon because of this sigma to the power 0, union 0, 1 because of sigma to the power 1. Then I can take combination 0, 0, 0, 1, 1, 0, 1, 1 because of sigma to the power 2. Keep moving, keep adding 0, 0, 0, 0, 0, 1 and so on because of sigma to the power 3. Dot, dot, dot up to infinity. So I'll keep on taking union of all these and ultimately I can take union of all these sets which gives me epsilon 0, 1, 0, 0 and so on. Right? So this star operator indicates that I am having 0 to infinity. And this star is also called as Klein's closure or star operator. So we'll be making use of this star operator quite frequently in this discussion. Once we have studied star, there is another operation that is called as plus. This plus is also called as positive closure. Now what is the difference between star and plus? As I said, star indicates 0 to infinity, whereas plus indicates 1 to infinity. What does it mean? When I am writing star, I am going to include a string of length 0, whereas in case of plus, there is a string of at least length 1. You are not allowed to have a string of length 0 in case of plus or positive closure. So how can I write? Sigma to the power plus is equal to sigma to the power 1 union sigma to the power 2 union sigma to the power 3 and so on up to infinity. But if you can observe here, we have not included sigma to the power 0 because positive closure allows string with length at least 1. 0 is not allowed. Now, whatever we have seen sigma to the power 0 and sigma to the power 1, if I try to have some relationship between sigma to the power 0 and sigma to the power plus, I can write sigma to the power plus is equal to sigma to the power star minus epsilon, because this includes epsilon whereas sigma plus doesn't allow epsilon, and that's why I can write sigma plus is equal to sigma star minus epsilon, or I can write sigma star is equal to sigma plus union epsilon, because sigma plus does not include epsilon whereas sigma star includes epsilon. Now let's talk about a language. We have discussed alphabet, we have discussed string. Alphabet, finite collection of symbols. String, finite sequence of symbols. Okay. Now talking about the language. It is collection of strings. I'm not saying it is finite because languages are usually not finite unless and until you specify some restrictions, some constraints on that. For example, I'm talking about binary. So I said that 0 and 1, sigma is equal to 0 and 1. Now if I write language, it will consist of any combination of 0 and 1. So there can be epsilon, there can be 0, there can be 1, any combination of 0 and 1 up to infinity. That is a language. Okay, so formal definition of language, it says that it is any set of strings over an alphabet sigma star is called as a language. I'm not commenting whether it is finite or infinite. Okay, but if you apply certain constraints on this, in that case it might become a finite language. Let's take an example of language, another example of this. So the formal definition of language, it says that infinite languages L, so it is infinite. Okay, L is equal to W belongs to sigma star such that W has a property P. I'm going to apply certain property on that language, ultimately on the strings, those who are present in that language. So it says that L1 is equal to W belongs to 0, 1. That means I'm going to have this W is nothing but a string, and that string is made up of 0 and 1. When I write star, any combination of 0 and 1. Okay. What is the property? W has an equal number of zeros and ones. Let's not go into more details of this, but for time being, what I can say is W, that string must have equal number of zeros and ones. So how can I write this L1? L1 is equal to equal number of zeros and ones. I can write epsilon also because it consists of 0 number of zeros and 0 number of ones. So epsilon is part of this language. Then I can have 0, 1. I can have 1, 0. I can have 0, 0, 1, 1. I can have 0, 1, 0, 1. Right? I'm not commenting on the sequence of these zeros and ones. What is been commented here is the equal number of zeros and ones. How many strings? Again, it can be infinite. This is called as a language. So my point was, this language consists of infinite number of elements, infinite number of strings. So that language can be infinite, that language may be infinite, but whatever the strings that in that language are there, each and every string is a finite sequence of an alphabet. What is alphabet in our case? It is 0, 1. So this is called as a language. Now if I apply some constraint on this particular language, what is that? It should consist of strings, that language should consist of the strings whose length is equal to, let's say, 3. Now, how it can be? Like, let's say if I write L2 is equal to, it consists of strings which are made up of this 0 and 1, but their length should be equal to 3. So if I write 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. That's it. So total I got 8 elements, 8 strings in this language L2. Now in this case it becomes finite. So if I apply certain constraints on that language, in that case that language might be finite. If you don't apply any constraints, that language can be infinite. With these prerequisite terminologies, let's come to the definition of finite automata. This finite automata is also called as finite state machine. So FA or FSM, both these terminologies are same. Now let's have a look at the formal definition of this finite automata. What it says that it is a 5 tuple. It has got 5 elements into that finite automata. What are those 5 tuples? Q, sigma, Q0A and delta. Now what each of these elements are? So Q is nothing but a finite set of states. I'll be having certain states into this finite automata, so that set must be, that number of states must be finite. Sigma, we have seen it is an input alphabet. So sigma is a finite set that we call it as alphabet. It is finite set of symbols. Q0, it is the starting state. But remember, we are writing Q0 belongs to Q. So obviously that initial state must be from the set of states. Then A, it is called as accepting state, or sometimes it is called as final states. Okay, so it is basically a set of, or you can say finite set of final or accepting states. And that's why we write A is a set, but again there is a constraint on that. A is, it should be a part of our set of states. So we write here A is subset of Q. So it is set of accepting states or final states. And finally delta. Delta is a function from Q into sigma and it gives to Q. That is called as a transition function. Okay. To understand this in better way, let me take one example of electric switch. Imagine electric switch, it is in some state, we call it as it is in off state. We'll apply some input on this. So I call it as push. Once I push this electric switch, it will enter into another state that we call it as on state. Now, switch is in on state, I want to switch it off. So what I'll do, again, I will push this switch and it will enter, it will transit into off state. So here I am showing the transition. So this becomes a transition diagram. But this transition diagram is not complete. Why? Because I need to tell that what was the initial state. Because sometimes my electric switch might be in off state initially or it might be in on state initially. So that initial state we have to indicate by this incoming arrow. There has to be exactly one initial state in your finite automata. And that's why we write Q0 is an element of capital Q. So it is start state or it is also called as an initial state. Then what I wanted to do, I wanted to switch on a particular appliance. So that is called as an accepting state, which is indicated by this double arrow or double circle. This becomes an accepting state or final state. There can be multiple final states in a finite automata. There can be multiple accepting states in a finite automata. So that's why it is a actually set. So A is the set of accepting states. So we are clear with this Q. I can write the definition of each of these elements of the finite automata. Q is equal to, I can write off and on. These are the two elements of Q. Then comes is sigma. What is sigma in our case? Input. So input we have applied is push. Next is Q0. We have already decided that okay, off will be the initial state. So I can write Q0 is equal to off. What is A? A set of accepting states. Now in our case, on is the single accepting state. So these four tuples are there. Now let's talk about the final tuple that is called as delta, transition function. How can I define this transition function? Here I'll write delta of. Where I should start? I should always start with an initial state, or I should always start with a start state. What is the start state? Where is that initial state? Look into Q0. It is off. So I will write off state, and then I need to apply a transition, we need to apply an input alphabet, that is sigma. If you look into the definition, Q I have written off, I need to apply this sigma on this. So what is sigma? Here it is push. I will apply push. Okay, and it will take me to the next state, that is again from Q. What is that next state? Follow some transition. Off, push, it will take me to the on state. So I will write down on. This is the transition. That is nothing but the transition function. So this is how we can define the transition function. Let's write down another transition. If I write on, now let's say on is the present state. It is also called as present state or current state. Now on state, if I apply push, I will transit into off state. Okay, so these are the transitions, and this is defined with the help of a transition function, that is delta. So these are the 5 tuples we need to define when we construct a finite automata or finite state machine. Now, to understand more in detail how this finite automata works, what I have done is I have taken a simple example of finite automata. Initially, don't worry about how this finite automata comes or what this finite automata does. We'll not worry about it. Okay, we'll take straight away a string. Finite automata is also called as an acceptor, or it is also called as language recognizers. That means it will tell whether this language is accepted or not. What is language? Collection of strings. So what I will be doing is I'll be taking one string from that language. Okay, so let's say I have taken a string called as 0, 1, and this is given finite automata. So as I said earlier, don't worry how this finite automata I have written or what this finite automata does. What we will do now, we'll try to process the string on this finite automata. I have written all the transitions, but before I move on to these transitions, I'll try to write down these transitions here itself. So I'll write down delta. Where I should start processing a string, always look into initial state. Okay, so I can say that Q1 is initial state because there is an incoming arrow, whereas Q2 is an accepting state because Q2 is encircled twice. There has to be exactly one initial state, but there can be multiple accepting states. Now let's begin with Q1. Now Q1 becomes my present state or the current state, and whatever string is given, I'll start processing one symbol at a time from this string. So let's say it is 0. I'll say Q1 0. Now if you look into the transition diagram, Q1 0, follow this transition, it will take me to state Q2. Sorry, it will take me to state Q1, not Q2. There is a self loop. Okay, now on Q1, let's apply another symbol, that is 1. So delta of Q1 now becomes current state 1. Q1 1, Q1 1 will take me to Q2. Okay, I have completely processed the string. What I'll do, once I'm done with the string, I will check in which state I am. I'm in state Q2, and if Q2 is an accepting state, in this case, yes, it is an accepting state. Q2 is an accepting state, so I can say that whatever string given to me 0, 1, this string is accepted. So this finite automata will tell me whether a string is accepted or not. Let's take another string, another input string. I can write 1, 1, 0. Same way we'll repeat delta of Q1 1. Okay, look into the transition. Q1 1 will take me to Q2. Here I write Q2. Now Q2 becomes current state. I'll write Q2, and the next symbol will be 1. Q2 1, there is a self loop. I'll remain in state Q2. We'll process the next symbol 0. So it is Q2 0. Q2 0, you follow this particular transition. Q2 0 will take me to state Q3. If you observe this Q3, before that I have completely processed my string. Now once I'm done with the string, I'll check the state. I'm in state Q3. As Q3 is not an accepting state, I conclude that string is not accepted or string is rejected. This is how our finite automata tells that whether a particular string is accepted or a string is not accepted or rejected by a finite automata. And that's why this finite automata is also called as an acceptor or language recognizer. Yeah, this is just processing of the string which we have already taken care of. Another string 110. So 110, it is rejected by the finite automata. Once we are clear with transition diagram, so what this transition diagram tells us, you can see it tells us about the states, it tells about the transitions, it tells what is the initial state, what all are the final states, or what is the final state, because there might be multiple final states in some cases. In this case, there is single final state. Now, this transition diagram we should be able to convert into a transition table. So how this transition table can be written? You can see there are certain rows and columns. So these states we can say these are the present states or current states. I can write here present state will do, or just states will also do. Now whatever present states are there, we can write all these present states like Q1, Q2 and Q3. I have enlisted all the present states. But sometimes they will not give you the transition diagram. We will be having the transition table. So from this transition table, I should be able to understand what is the initial state and what is the final state or accepting state. So to indicate an initial state, we will be having again an incoming arrow, which indicates that yes, Q1 is an initial state. Similarly, to indicate an accepting state, we will be having a star before that particular state. Sometimes there can be a circle. So either star or circle, both will do. Okay, I mean any of these two will do. You can have star or you can have a circle, which indicates that yes, it is an accepting state. And third Q3 is there. Now this is about the present states. Now next states. So next column will be of next state. In next states, I'll be applying whatever sigma is there. You can easily understand what is sigma. It is 0 and 1. I'll have 0 and 1. Now on this state Q1, what happens if I apply 0? So you can see on Q1, if I apply 0, I will reach into state, I will transit into state Q1, no change in the state. Then a column of 1, that is second alphabet, Q1, 1. So it is Q1, 1. What happens if I apply 1 on Q1? Q1, 1, it will take me to state Q2. Go ahead, Q2, 0, Q2, 0. You can see it will take me to state Q3. Q2, 1 is, Q2, 1 will remain in the same state because there is a self loop. And finally Q3, 0. Q3, 0, it will take me to state Q2, and Q3, 1 will take me to state again Q2. On this next state columns, we need not indicate the initial state, we need not indicate the final or accepting state. That is to be indicated on the present state column itself. But remember, this circle and star both are not required. Any one of these two. I just shown for simplicity point of view. Now one more example we will take to build a transition table. This is given the transition diagram. Okay, from this we can easily understand there are three states, A, B, and 1, 0 is a state. These are not two symbols. This is a single state we have indicated, and A is an initial state, whereas 1, 0 is an accepting state. So while writing this, I can say present states. So I'll write down the present states. Whatever present states are there, I will enlist all these present states. So A, B, and 1, 0. Then to indicate initial state, you can see here A is initial state. I am having incoming arrow towards state A, and 1, 0 is an accepting state. So I have encircled here. 1, 0 is an accepting state or final state. Now here next two columns will talk about the next states. Sigma is equal to 0 and sigma is equal to 1. So A0, look into the transition diagram. A0, again there is a self loop. I will remain in the same state. A1, you can see here A1, it will take me to state B. I will write down that. Then B0, it takes me to another state, that is 1, 0, and B1 will transit in the same state. There is a self loop. And finally 1, 0, 1, 0, 0. 1, 0, 0, it will take me to state A. I am writing that state A. And then 1, 0, 1, 1, 0, 1, it will take me to state B. So there is an arrow from 1, 0 to B on 1. So this is how we can convert transition diagram into transition table, we should be able to convert reverse way as well. If you have been given transition table, we should be able to convert it into transition diagram. That's all for today. Thank you all.